beginning a new unit over thermochemistry, so you need to have out your green notes that you picked up today, as well as your white homework packet, and be prepared to take notes and follow along, please. Okay. Your notes begin with comparing and contrasting the idea of exothermic and endothermic reactions. It says thermochemistry is the study of heat changes that occur during chemical reactions and physical changes of state. Okay, so far in this class, we have emphasized heat changes from physical changes of state. Okay, you may remember the phase change diagram, and this is where we measured heat changes between phase changes, so solids, liquids, gases, etc. Okay, in this unit, we're going to use a different diagram that emphasizes heat changes during chemical reactions. Okay, so now we're into the more chemical side of chemistry. Okay. It says, in an exothermic process, heat flows from the system to the surroundings. Know that the system is the part of the universe on which you're focusing your attention. The surroundings are everything else. Okay, so since we're talking about chemical reactions, in an exothermic process, the system will be the chemical reaction itself. And the surroundings will be everything else, like its container or the air around it. Okay, so for example, I want to play a video for you. Okay, and we're talking about exothermic, which is this one. Okay, now in this video, we've got potassium permanganate, which is this black powdery stuff, and someone's going to add glycerin to it. Okay, so observe what happens. Okay. Going back to your notes, I want to draw a picture of this. Okay, we have potassium permanganate and glycerin that are reacting. So I want to go ahead and write that down for you. Plus glycerin. Okay, and the glycerin, I'm just going to draw a black circle. Okay, and once you add the drop of glycerin to the potassium permanganate, it begins to react. And in this reaction, heat flows from the reaction to the surroundings. Okay, so this is the flow of heat. Just like we said in an exothermic process, it's supposed to go from the system to the surroundings. Okay, so in this situation, the surroundings, meaning the things outside of the chemical reaction, will feel hot. Okay? An endothermic process is just the opposite. It's when heat flows from the surroundings to the system. So again, I have a video, so let's watch the video of endothermic. Okay. In the beaker is ammonium thiocyanate. And they add barium hydroxide octahydrate to it. So the reaction's endothermic. The temperature drops as heat is absorbed. Okay. The beaker is frozen to the wood. Okay, so let's draw a diagram of this in our notes. Okay, and we're in endothermic now. Okay, I have my beaker. Okay, and in the beaker, I have a chemical reaction taking place between ammonium thiocyanate and barium hydroxide. It was octahydrate. That just means it has water molecules in between its structure. Okay, so when these two chemicals react, the water that he poured onto the wood originally froze. Now, why did the water freeze? The water froze because this is an endothermic process. And in that endothermic process, heat flows from the system from the surroundings to the system. So this time it's flowing in this direction. Okay? So if heat is lost from the surroundings will feel cold. Okay, so this time the surroundings, meaning the water and the wood, are going to feel cold. Okay, so let's try a couple on your own. I have two examples here for practice. Number one says you have a person, and the person's the system. This person is sitting next to a campfire. Is the system exothermic or endothermic? The second scenario is you've got the system again being the person, and this time the person is perspiring, meaning they're sweating. Is this system exothermic or endothermic? So what I want you to do is to work with your neighbor for 1 minute, and I want you to draw a picture of a person in this campfire. I want you to show me what's happening with heat and to label if it's exo or endo. So for the first and the second practice question, you have 1 minute. Okay. Okay, bring your conversations to a close, please. Okay, and number one, okay, you have the person, and this person is sitting next to a campfire. Okay, now the fire is the thing producing heat. So heat is flowing towards the person or towards the system. So if heat is flowing towards the system, this is an endothermic reaction. Okay? For number two, here's my person again. This time my person's sweating. So heat is flowing away from the person, making this an exothermic reaction. Okay. It says, according to collision theory, atoms, ions, and molecules can react to form products when they collide, provided that the particles have enough kinetic energy. Particles lacking the necessary kinetic energy to react bounce apart when they collide instead of reacting. The minimum amount of energy that particles must have in order to react is called the activation energy. So underline that. Okay? So what allows them to react is this activation energy. Think of activation energy as a barrier that reactants must cross in order to be converted into products. The activated complex is the name for the arrangement of the atoms at the peak of the activation energy barrier. It is an in-between state, being neither reactants nor products. Okay, so before I go in depth into explaining what all this means, I want to play a YouTube video that illustrates this occurring.
Mixed together in the same container, they collide. But there is no reaction until a spark or flame is added. Why? To react, the molecules must collide with sufficient energy to break the oxygen-oxygen bonds and carbon-hydrogen bonds so new bonds can form. The additional energy needed to break existing bonds and start the reaction is called activation energy. An energy diagram can help show these energy changes. Initially, the oxygen and methane molecules collide but do not have sufficient energy to react. A flame can supply the activation energy needed to start the reaction. At this point, bonds break and new bonds form in an exothermic reaction that releases energy. The energy released supplies the activation energy for other molecules to react, and the mixture explodes. In the air, nitrogen and oxygen are continually colliding but lack sufficient energy to react. Heat from lightning supplies the activation energy to break bonds, and new bonds form in an endothermic reaction that absorbs energy.
Okay, so hopefully you followed that video a little bit. If you go to the next page in your notes, I'm going to explain this more in depth. It says in an endothermic reaction, the reactants have less potential energy than the products. So delta H is positive, okay? Delta H being right here, okay? Now what I want you to understand about delta H is that we call delta H the enthalpy. Okay, and what this means is it's the heat of the reaction. Okay, and you get delta H, meaning heat gained or heat released, when you subtract the energy of the products minus reactants. Okay, so if you look at this diagram, okay, everything's labeled for you. You've got your activation energy that's labeled. You've got the activated complex, which is like your in-between state, your reactants, your products, etc. Okay, so if we were to give our y-axis, which is the potential energy, a scale, okay? Let's say I label right here 0, right here 5 kilojoules. Let's see. We'll do right here will be 10 and 15 here, okay? So it's not complete, but it's good enough for the purpose in which I'm going to use it. So let's say that's our scale, okay? And I'm trying to figure out what the delta H is, meaning the heat of the reaction. Is heat released or is heat absorbed? So the value for products is 15 kilojoules, but the value for the reactants, or potential energy for the reactants, is 5. Okay, well 5 minus 15 gives me a delta H that is positive 10. Okay, now it's important that you know that this is a positive number because when delta H is positive, like it says in your notes, this indicates an endothermic reaction, meaning energy must be supplied or absorbed by the reactants to raise the particles up to the higher energy level. Okay, so it's at a higher energy level. You can see that. Okay, the products are above the reactants. In order for this to happen, energy has to be absorbed. So I need you to be able to look at a diagram like this and see that there's a change in energy right here, and that because the difference is positive, it's endothermic. Okay? Let's look at the exothermic reaction. Okay? Again, here you have your reactants. They're always first. Your products are down here at the bottom. Now, you still have an activation energy, meaning you still have this hill you've got to get over, right? However, this time, the products are located below the reactants on the potential energy scale. So again, if I add that scale that I had on the first one, so 0, 5, 10, and 15, and I'm measuring the delta H, or enthalpy, which is products minus reactants. This time the products are 5 kilojoules, and the reactants are 15 kilojoules. So this produces a delta H that is negative 10. Okay, so this sign, positive or negative, is very significant when we're talking about chemical reactions. It says if delta H is negative, we're going to have an exothermic reaction because the extra energy is released to the surroundings. And that makes sense because if it's exothermic, it feels warm. Okay? So what I need you to be able to do is to look at a diagram like this. See that if the reactants are higher than the products, that means energy is released and it's exothermic. Okay? Okay, so I want you tonight for homework, because we're going to stop here. Tonight for homework, I want you to work on the page in your homework packet called Over the Hill. And I want you to work on this front and back for the rest of class and for homework. Okay? You can work with a partner if you would like to, as long as you're behaving well. And this worksheet that you're going to be working on, it makes you think, okay? So think about your answer choices. Be logical about them. We'll cover them tomorrow in class, but this is going to require you to think quite a bit, okay? So you're doing over the hill, front and back, okay? I will see you tomorrow. Have a great rest of the day.